Thank you, Professor Toyama, for introducing. So, am I audible?
Yes, and you can switch to the presentation mode.
Yes. Sorry, I could not find the presentation. Yeah. So, is it visible now?
Yes.
Okay. So, good morning, everyone. So, today I will be discussing about strain-tuned magnetism in flexible palladium cobalt C60 thin film. And before going to the talk, I would like to thank the organizer of this conference for giving me this opportunity to present my work here. So first I will briefly discuss about the motivation and objective behind this work. So in case of heavy metal ferromagnet based thin films, the inversion symmetry gets broken at the interface due to which in presence of the strong spin orbit coupling of the heavy metal layer, an asymmetric exchange interaction comes into play, and this exchange interaction gives rise to a canted spin state of the ferromagnetic spins nearby the interface. And this DMI interaction can be represented using this Hamiltonian as shown here. Here D is the DMI constant and SI are the neighboring spins. Now, if you consider with respect to the ferromagnet layer, the heavy metals are symmetric on both the sides, then the DMI gets mostly cancelled out. However, if the heavy metal layers are different, as shown here, like palladium and tungsten, then the DMI can be a finite amount, and that can be very useful for the hosting of chiral spin structures and also skyrmions. So there is always a search for alternative DMI host materials, and in this context, light atom-based molecules are highly promising. So there is a recent demonstration where graphene has shown the emergence of DMI when deposited on top of cobalt, and in this case, because graphene is composed of light atom carbon, but here the Raspberry effect gives rise to the Raspberry DMI, due to which we can get a finite DMI from a ferromagnet and graphene interface. So inspired by this, carbon has other promising allotropes as shown here, like carbon nanotubes fullerenes, and they also have some curved structure due to which there is a curvature enhanced spin orbit coupling exists in these allotropes. Now we are particularly interested in fullerene, that is an interesting molecule that is composed of 60 carbon atoms, and here if you see, each carbon atoms form covalent sigma and pi bond with its neighboring atoms. Now, this pi and sigma bonds gets hybridized with each other because of the curved structure, and this gives rise to an enhanced curvature enhanced spin orbit coupling. Now, in this work, we aim to find out if there is any enhanced domain wall velocity and DMI due to such heavy metal ferromagnet and C60 structure, and further to tune it via strain. So in this context, we have prepared an asymmetric sample structure as shown here, and by varying the thickness of C60 from 0 to 1.6 nanometer. Here, all the metallic layers are deposited via DC sputtering, and whereas the organic layer is deposited by thermal evaporation technique. So after preparing the samples, we have measured the hysteresis loop using polar microscopy, and it shows a continuous decrement in coercivity due to the decrement in magnetic anisotropy in the samples with increasing the thickness of C60. Further, we have measured the domain wall velocity in these samples. And before going to the results, I will briefly discuss about different region of domain wall motion and then the domain wall measurement protocol. So in case of a ferromagnetic thin film, the magnetic domain wall acts as an elastic interface that moves through a two-dimensional disorder media. Now, the domain wall motion in such case can be divided into three regions, that are creep, deepening, and flow. And in case of creep region, the application of a very low magnetic field or force mainly gives rise a domain wall motion that is governed by the pinning potential and thermal energy that are present in the system. However, when the applied force is greater than F deepening, then the domain wall motion enters in a deepening region, and here mainly the applied force drives the domain wall over the pinning potential. With the further application in the applied force, the domain wall enters into a flow region where it becomes free from the pinning parameters and shows a linear enhancement in velocity with the applied force. Now, in our work, we have measured the domain wall velocity mainly in this creep region, and in case of creep region, we have followed a pulsed magnetic field induced domain wall measurement protocol, and there is a schematic of the measurement protocol where first a saturation magnetic field is applied, and the background can be look either like black or white as shown here, and then we apply a nucleation pulse field in the opposite direction to get a domain nucleated as shown here, and after that we apply next pulse field for the propagation. This helps to propagate the domain, and we capture the images of this nucleated and propagated domains. Then we subtract these two images and get a displacement that is divided by the pulse width to get the domain wall velocity. We have performed this domain wall velocity measurement for the both sample, that is with C60 0 and 1.6 nanometer. Here, interestingly, you can see that the domain wall velocity, if you look at the y-axis, in comparison to the 0 nanometer sample, the 1.6 nanometer sample has a 2-order increment in the domain wall velocity. Now, to know the exact reason behind this increment in velocity, we have fitted this domain wall velocity data with the creep graph as shown here. So, in the creep region, velocity follows the exponential relation with the applied field, and logarithmic of velocity follows a linear relation that is plotted here. By fitting, we found that the deepening parameter of the sample is actually reducing upon application of this, upon increasing the C60 thickness. And this reduction in pinning parameter helps in getting a higher domain wall velocity. In addition, the reduction in effective PMI helps in increasing the domain, help in decreasing the domain wall formation energy, which in turn gives rise a higher domain wall velocity. Now, further, if there is an enhancement in DMI, that also could get a higher domain wall velocity. So, in order to find out if there is a higher DMI in our sample or not, we have further performed the domain wall velocity measurements in presence of an in-plane field that gives rise to asymmetric domain expansion when the DMI is present in sample. So, this is the measurement protocol where the like previous measurement, we have also nucleated domain, and during propagation we have applied both a out of plane pulse field and in plane DC field. Due to this, if the system has a DMI, then the asymmetric domain propagation will occur. This is due to for a particular applied field value, the domain wall either gets a addition of HX plus HDMI, or it gets a cancelled of the HX field, due to which the propagation is different at both the sides. Now, the velocity of this left and right wall can be plotted, and the minimum of the velocity represents the DMI field. By using this, the effective DMI can be calculated. In our case, we have measured the velocity versus in-plane field for such two samples and found that the minimum of the velocity for the palladium cobalt palladium sample is at 8 millitesla. Due to this symmetric structure, it gives rise to a very low DMI. However, for the palladium cobalt C60 sample, the HDMI is around 53 millitesla, which gives rise to a finite DMI from the samples. So this is promising because of the sample heavy metal ferromagnetic fullerene shows a finite DMI, and also by preparing a control sample, we found out that the cobalt C60 interface gives rise to a finite DMI that is 0.1 millijoule per meter square. To further tune such magnetic properties of the palladium cobalt C60 samples, we have prepared them on a flexible polyimide substrate, and we have used this flexible substrate to generate a systematic strain upon which we want to study the magnetic properties. To apply strain, we have used molds of different geometries like convex and concave shape. And here, when the sample is mounted in a convex mold, then it generates a tensile strain on the thin film. When it is mounted on a concave mold, it generates a compressive strain on the thin film side. Now, the magnitude of the strain can be measured using this equation. Epsilon is T by 2R, where T is the film thickness and R is the radius of the mold. By finding the radius of the mold, it can generate a different strain on the sample deposited on the flexible film. This is a picture showing a flexible magnetic thin film that prepared in our lab. Now, after preparing the samples, we have measured the magnetic hysteresis loop at the unstrained and compressive and tensile strain state of the sample. It is shows that under compressive strain, the coercivity decreases. However, under tensile strain, the coercivity increases. Further, we have taken the coercivity of such hysteresis loop by varying the strain systematically up to 1% and found that under tensile strain, there is a systematic increase in coercivity and a systematic decrement in the coercivity under compressive strain. So to understand this happens because of the magnetoelastic anisotropy energy that induces in the system under the application of strain. Here lambda is the magnetostrictive coefficient and sigma is the applied stress. So when for a cobalt palladium system, lambda is actually negative, and in case of tensile stress, sigma become positive, due to which lambda sigma product become negative. Now to minimize the magnetoelastic energy, it in turn induces an easy phase along the out of plane direction that increases the PMA. When PMA increases, that in turn gives rise to a slight increment in the coercivity of the sample, and that can be seen here. Under compressive stress, it leads to a decrement in PMA and hence a decrement in coercivity. So such effects of strain on the magnetic properties is also known as Villard effect or inverse magnetostrictive effect. And within the elastic limit, all such changes are reversible in nature. So further, we have measured the domain velocity under strained state. As compressive strain reduces the PMA of the sample, so we thought of getting a higher velocity under compressive strain, and similarly, we also see by experiment that around 14 millitesla, there is a 2-time increment in the domain velocity, and this 2-time increment can be justified with respect to the pinning parameters that is reduced under the compressive strain, and also the magnetic anisotropy that is also reduced when we consider the magnetic compressive strain applied on the sample. From this, we can say that strain engineering can be a very promising tool for manipulating the magnetization reversal, magnetic anisotropy, and also domain dynamics in the flexible film, and can act as a very promising tool to tune the functionalities of spintonic devices to the desired level. So I would like to thank my supervisor, Professor Shubhankar Vedanta, my collaborators, and all lab members for their continuous support throughout this work. And I would like to also thank the funding agencies for their support to carry out the experimental work. And thank you for your attention.
Thank you very much for your nice talk. So since the time is limited, if you have a short question, we can accept one. Otherwise, you can discuss in the gather town later after the session.
Sure, we can discuss.
Okay, if not, we'd like to conclude the session. So thank you very much for your presentation.
Thank you.